And for me, concepts is a great drawing ground for cross-disciplinary inspiration and techniques in audio. And it really becomes like there's a lot of really great procedural audio work or improvised audio, interactive audio work going on in the field of sonic arts. But there's a lot of these different concepts of procedural audio in games, but there's just a heck of a lot more there. And this field, sonic arts has been going on since like the 50s, 60s. For example, great composer called Wratt was building like 200 speaker domes in the 1960s. Like 60s anyway. So there's been a long history of fantastic and very strange things. So next up, what is procedural audio? I'm sure a lot of you have come across games like No Man's Sky and things. So this is all kind of part of the field of procedural audio. Procedural audio is non-linear, often synthetic sound created in real time according to a set of programmatic rules and live input. And in my talk today, I'm really going to be focusing on the synthetic sound part of this. So to me, I'm really interested in creating procedural audio from scratch, from kind of a C and C++ level via digital signal processing. So I'm going to quickly run you through some of the ways in which you can do that. Audio created, organized in real time. Real time that's important. Changes based on certain game parameters, so we can apply things from the game to drive our synthesis engine, drive our audio engine. Usually we split that within the field of games, you split it into procedural music and with the game, or kind of the emotion of the game as it happens, potentially. And because of this, we can really get nuanced interactions between the player and the audio in the game, almost like the game is improvising, like a improvising musician playing as the player plays the game. So this is kind of how I like to view procedural audio. But what are some of the problems? Now, first up, it does use a lot more, or it can potentially use more CPU, so you end up with a memory CPU trade-off when you move into procedural audio, because you are dealing with like real-time, like really sometimes quite intensive digital signal processing happening at quite a low level that can show up the CPU. Multi-platform, for the same reason, because it has to be at such a low level and running in real time, multi-platform support can become difficult. So whereas often building a game, you can work in, say, Unity and C#, and Unity will deal with all your cross-platform problems. Often in procedural audio, we have to go a little bit deeper and write in things like C or C++, and that aren't necessarily, like Unity can't just deal with all of the multi-platform support for us. So, worth bearing in mind. Next up, the tools are quite limited at the moment in the field. There's not a huge amount of available commercial tools or free tools, really. There's bits and pieces that I'll show you soon, but really, if you wanted to get deep into procedural audio, you do have to have some, they have to have a good coder hanging around, or be a good coder yourself. And one problem is that there are potential licensing problems on certain parts of synthesis. Now, a lot of this hasn't been enforced historically, and so don't freak out, but for example, Stanford University owns patents on a lot of synthesis techniques that get commonly used right across the field of sonic arts and procedural audio. So just worth keeping an eye out for that in the long run. So what are some of the techniques that you can use in procedural audio? Synthesis is obviously really the core one, so I'm just going to run you through some of the different types of synthesis that exist in the field. So first up, we have our basic waveforms. These are the bog standard ones that have been around for an awful long time. We've got the sine wave. I'll show you all what a sine wave looks like, but in terms of an audio signal, it sounds like. That's just one individual harmonic signal at a single frequency. And that's kind of the most basic building block for a lot of audio synthesis. On the other end of the spectrum, we can look at more harmonically dense signals, such as the sawtooth wave. And this one has got, rather than being a single frequency, like a sine wave, this has got multiple. Due to the way in which it gets played back, it ends up having multiple harmonics going upwards, and it's quite harmonically dense. We've also got things such as noise signals. I'm not going to play all of these. Triangle waves, square waves and pulse waves. And these kind of form the foundation of audio synthesis. And a lot of the early video game engines, audio hardware for games was just using basic things from this list. For example, the Nintendo Game Boy was capable of playing 2 pulse waves and a noise wave at the same time, and also had a kind of primitive wavetable playback I'm not going to go into. But yeah, these kind of formed the foundation for a lot of the early synthesis in games. And then, and in Sonic Arts, this is really foundational stuff. Then we develop kind of more complex tones, or more complex types of synthesis. We've got things like additive synthesis. I'll show you examples of these in a sec. Subtractive synthesis, FM synthesis, AM, and gradient synthesis. And here's an example. So, this is a piece of software called MaxMSP, which is a fantastic piece of software for, it's mainly used in like audio installation work and art installation work from a kind of Sonic Arts perspective, but is really good procedural audio software. Sadly, the licensing makes it very difficult to embed in a video game, which sucks. Anyway, here is, so additive synthesis is the first one I'm talking about. Additive synthesis is when we take simple waves, such as sine waves, add them together to make a more complicated wave. And here's an example of how it sounds. So, first up, we can take a basic wave. Down the bottom here, I've got a spectrograph, so that's frequency on the X and amplitude on the Y. That's a fundamental frequency, and we can add signals above that. So at the moment, we can kind of think of that like a chord, like it's got lots of different notes that are all gone up like a chord. But if we move the signal, all of a sudden now it groups all of that together as what we call an audio timbre, which is the overall sound of it, and actually becomes its own individual voice in a way. And this technique is particularly useful in things like, say, physical model synthesis, where you take some kind of model of the way maybe an instrument works, and we can recreate that using basic ways to create the kind of sound we expect from that instrument. This was very popular in kind of early synthesizers as an approach. And the other popular approach in early synthesizers was subtractive synthesis, kind of the opposite way around, hence the name. This is where we take a complex tone, such as that saw wave we heard before. So I'm going to play the saw wave. Here we go. So this has got a lot of high, I should put a spectrum back up, but it has a lot of high pitch information. It's really bright. And we can jump in with a filter, and filter out some of that high pitch information. Oh, my filter's gone way off the chart. Sorry. There we go. So that cuts out all that high pitch frequency, we can pull it out. And we can move the note around. So change the tree a little bit to get interesting harmonics. And so subtractive synthesis basically means taking some kind of filter and applying it to a complex waveform, whether it be noise or it could be really anything. And this was also very popular in things like the Moog synthesizer as a really interesting way to get quite dense and interesting harmonic. Sorry, was that a question?
Oh, yeah, just wondering what set Q is.
Oh, sorry. So Q is, at this stage is just basically deciding how steep the roll off of frequency is. It's something I probably shouldn't have included on the slides. And then we can use subtractive synthesis for things like physical modeling synthesis to make this quite interesting thing from Andy Farnell, which is a kind of wave synthesizer, also wind synthesizer. Using noise signals, moving filters, you get quite a good synthesis of wind with very minimal, I think it's on like 0.8 CPU or something. 2 CPU, but that's everything running at the same time. So I'd say pretty usable in a lot of situations. Okay, but enough time to speed through this. Another type is FM synthesis. This is where we take a basic wave and we change the frequency of that wave very quickly. So if we take a wave affects C, and changes frequency as pitch. So pretty slow it sounds like that. Wow. But if we speed that up, all of a sudden we get a really interesting effect. And we can move that around. So all those crazy sounds are just created by moving the frequency up and down incredibly fast. And this became like a real sound of like the 1980s. To me, this is like the DX7 synthesizer was not exactly FM, but it was pretty much FM. Yeah, lots of really great music. FM, AM is pretty similar, but rather than changing the frequency of your signal, you just change the amplitude of your signal. Here's something like this. Okay, and finally we've got the real weird one. This one's called granular synthesis. Now this is a pretty odd technique, but pretty useful in certain situations. In this one we take an audio wave file and we randomize our playhead essentially. So we play lots and lots of little bits that are all mashed together. It sounds a bit like this. There you go. So we're taking the signal and we're randomly choosing bits of it to play. And then we can choose pitch. And this has been used a lot in, so maybe it sounds very odd in a music context, but for, say, taking an engine sound and trying to strip that out over time and change the pitch and things, it's a very useful technique. It's actually been used in quite a lot of racing games as a way to create really awesome sounding engines. So that's synthesis, and then another thing we can use to talk about procedural audio is procedural use of audio effects, which we go through that for those of you who aren't on the audio end of things. They go after the sound source in the signal chain and they affect the audio output in some kind of way. So for example, things like reverb, delay, chorus pitch shifts, filtering. So I'm going to blast through this stuff because I'm a bit of time. Lots of different types of effects that we can use to affect the audio. I'm going to give you a quick example of the kind of sound we could expect. One example of using it procedurally. So this is a game I worked on last year, and there's a bit of gameplay, and then I'll talk you through the. This is the gameplay. So what that was is playing the audio backwards, or playing audio file backwards, and also applying quite an intense low pass filter to it. Because if you speed up an audio file, all of a sudden the pitch increases as well. So I had to really intensely, basically follow as the speed got higher, follow the low pass filter, so it didn't feel like it was getting too bright. So that's just one thought. I mean, this is a huge amount. There's a huge amount of possibilities in procedural effects changes. Also, we've got procedural organisation or composition at a higher level than this kind of low-level stuff. We can use things such as interactive scoring techniques. Now, this is a whole field really, interactive scoring. So I'm not going to go too deep into it, but we're going to look at things like vertical remixing. I'm actually going to skip this example on here, but that's a technique where you take multiple layers of audio at the same time, and you can fade them out between different layers to create kind of a moving, changing composition. Cool, I use example, but another type is Markov models. This is a weighted random process. Kind of simplistic AI is really where it comes from. And in Markov models, we weight different random parameters, and we can also, by using different orders or being able to have our Markov model look back to previous states, we can kind of give it a basic simplistic memory in order to choose where it's going to go next. This is really useful for like melody creation and procedural audio. We can get great complex probability trees. It's used a lot in all those sort of applications, but it basically was in audio as well. Here's a quick example of something I was working on recently, in which I use a Markov model to create melodies over top of a backing. So there's a backing loop, and then over top is synthesized Markov melodies. But yeah, so as I hold down, it's actually quite hard, but as I hold down, I think on these things, it will go through and procedurally create notes in time. Also got extended techniques. I'm not going to actually skip this. Sorry, but there was just kind of some extended AI techniques. I'm going 2 minutes. But how to actually implement these things in games? Because all this stuff is great in things like Next MSP, but in terms of actually getting it to games, it's pretty difficult. For example, in Unity, we can't just use the built-in like update loops because they're not at an accurate enough level in order to be able to really synthesize audio. For example, your update and fixed update don't go faster than about, I don't know, get 50 milliseconds, 20 milliseconds, but audio is being synthesized at 44,100 samples per second potentially. So we can use things like the Unity audio mixer to do procedural effect mixing, but we can also jump down and use, there's a great function called on-audio filter read in C# that allows us to do sample level audio. There's also a native audio plugin SDK that's C++, like basic plugin development for Unity that allows us to write synthesis in Unity. This is a little bit crusher plugin I built last year. Unreal, like Unity, it has procedural audio effect mixing, and recently, as of 4.16, they've introduced a really cool synthesizer in there, so I can play with that. Middleware-wise, so why? For those of you who don't know, in audio middleware, there's kind of two big companies, Fmod and Wise, that both put out great software. Wise has a basic synthesizer built in with a MIDI implementation that allows us to do procedural audio, and Fmod doesn't have one, but both allow you to compile basically some URLs to procedural audio. Finally, we've got this great thing called Pure Data, which is essentially Max MSP but free, and we can write procedural audio in that, and then compile it into C code via, well, heavy libraries, real key way to do that. And I consider this to be the best, basically the best way we can deal with procedural audio at the moment, is writing it in here. This is actually how Sport against Sport to the soundtrack was via Pure Data. A little bit before he became out. Yeah. And conclusion, Sonic Arts and procedural audio games have many similarities and the fields can learn from each other. Procedural audio is really another tool in the toolbox. It has advantages, disadvantages. I'd love to see more tools that allow non-programmers to create procedural audio experiences in games. Really, the moment is very programming focused. And I'd also like to see more game projects from taking the challenge. Cool. Thanks, guys.